Hello everyone, and welcome back to our fifth lecture in our introductory course to quantum computing. Today, we'll be talking about the second quantum mechanical phenomena that helps quantum computers gain a quantum advantage over classical computers. And this quantum mechanical phenomena is quantum entanglement. So first, let's go over a quick overview of what entanglement does. So to create complete entanglement, we have to entangle two qubits together. We can entangle more than two qubits together, and this will create entanglement, but it won't create complete entanglement. Albert Einstein labeled quantum entanglement as spooky action at a distance. And essentially, when two qubits are entangled, theoretically, if we took one qubit to the end of the universe and the other qubit to the other end of the universe, by knowing the state of the first qubit, we would automatically know the state of the second qubit. So simply, entanglement is the idea that if you know the state of the first qubit, then you automatically know the state of the second qubit entangled with that first qubit as well. So now let's take a look at an entangled quantum state. At the top of this slide, we have our entangled quantum state with a 50% chance to collapse into 0, 0 when measured, and a 50% chance to collapse into 1, 1 when measured. But basically, what I want to illustrate with this state is that in this entangled state, there's only two possibilities. So if we know that qubit 1 is ket 0, then qubit 2 must also be ket 0. And if we know that qubit 1 is ket 1, then qubit 2 must also be ket 1. There's no other possibility for the second qubit to be. Bell states are simply quantum states that are completely entangled. As I mentioned in the overview, Bell states can only be achieved when two qubits are entangled with each other. There are 4 Bell states in total, and each Bell state has a different alignment of qubits that then have a C0 gate applied to them in order to achieve that Bell state. So, as I mentioned with Bell states, entanglement is created using the C0 gate. This is a 2-qubit gate and also has a matrix representation similar to our single qubit gates like the Hadamard gate, the X gate, and the Z gate. We'll spend the rest of this lecture explaining how the C0 gate works and taking a look at what happens to each state of qubit when the C0 gate is applied to it. So how exactly does the C0 gate work? The C0 gate has a target qubit and a control qubit. If the control qubit is 0, then the target qubit is unchanged, which means that nothing happens. However, if the control qubit is 1, then the target qubit is flipped, so it would go from 0 to 1 or 1 to 0. So let's say that qubit 1 is the control qubit and qubit 2 is the target qubit. When we take the state 0, 0 and apply the C0 gate to it, we get back 0, 0. The qubit 1 was the control qubit and it was in state 0, so qubit 2 is also left unchanged, returning us the original state. This is similar to what happens when we take the 0, 1 state and apply a C0 gate to it. Because qubit 1, or the control qubit, is in state 0, the second qubit, or qubit 2, is remained unchanged, giving back the original state. However, when the control qubit is 1, as in the state 1, 0, we would get back 1, 1, as the target qubit will flip because the control qubit is in state 1. And finally, when the original ket is 1, 1, we will get back 1, 0 after we apply a C0 gate to the 1, 1 state. So here is the C0 gate matrix representation. As compared to the single qubit gates, which are 2x2 matrices, the C0 gate is a 4x4 matrix. Each row has a bunch of zeros, or 3 zeros, and 1, 1. In the top row, the 1 is in the first position. In the second row, the 1 is in the second position. In the third row, the 1 is in the last position. And in the fourth row, the 1 is in the third position, giving us this 4x4 matrix. Now you might be wondering how we can actually multiply a 4x4 matrix with our original 2x1 matrices. However, we represent quantum states with two qubits slightly differently, in the fact that we represent them in a 4x1 matrix. So on top we have the 1 squared, which is the chance of collapsing into 0, 0. In the second position, we have the 0 squared, which is the chance of collapsing into 0, 1. In the third position, we have 0 squared again, which is the chance of collapsing into 1, 0. And in the final position, we have 0 squared, which is the chance of collapsing into 1, 1. So this state would 100% of the time collapse into state 0, 0 when it is measured. So in this first example, let's take a look at what happens when we apply the C0 gate to the 0, 0 state. On the left, we have the C0 gate matrix multiplied by, on the right, the 0, 0 state matrix, which, as I just covered on the last slide, is 1 on the top and then 3 zeros in the remaining 3 positions. When we multiply these two matrices together, we get 1 times 1 plus 0 times 0 plus 0 times 0 plus 0 times 0 on the top, 0 times 1 plus 1 times 0 plus 0 times 0 plus 0 times 0 on the second row, 0 times 1 plus 0 times 0 plus 0 times 0 plus 1 times 0 on the third row, and 0 times 1 plus 0 times 0 plus 1 times 0 plus 0 times 0 on the bottom row. Adding all these values up, we get 1, 0, 0, 0, which is the expected result, as this just means that the state was unchanged and we have a 100% chance of collapsing into the 0, 0 state. Now let's take a look at what happens when we apply the C0 gate to the 0, 1 state. As per usual, on the left we have the C0 gate matrix, and on the right we have the 0, 1 state matrix. When we multiply these two matrices together, we get 1 times 0 plus 0 times 1 plus 0 times 0 plus 0 times 0 on the first row. On the second row, we have 0 times 0 plus 1 times 1 plus 0 times 0 plus 0 times 0. On the third row, we have 0 times 0 plus 0 times 1 plus 0 times 0 plus 1 times 0. And on the final row, we have 0 times 0 plus 0 times 1 plus 1 times 0 plus 0 times 0. When we add all of these values up in each row, we get back the matrix 0, 1, 0, 0. This means that we have a 100% chance of collapsing into the state 0, 1 when measured, which is correct, as our control qubit is 0, our target qubit is 1, so therefore the target qubit is left unchanged, and we would get back the state 0, 1. Next, we can take a look at what happens when we apply the C0 gate to the 1, 0 state. You all probably know the drill by now, and we multiply the two state matrices together. When these two matrices are multiplied, we get back the matrix 0, 0, 0, 1, which actually is expected, as our control qubit is 1, which means that our target qubit 0 will flip after the C0 gate, is applied to it. Therefore, we would get back the state 1, 1 with 100% certainty, and that is what we see with the matrix. Finally, we can take a look at what happens when we apply the C0 gate to the 1, 1 state. Like usual, we just multiply the two matrices together, and in the end, we get back the matrix 0, 0, 1, 0, which means that we have a 100% chance of collapsing into the state 1, 0, 1 measured. This makes sense, as our control qubit is 1, and our target qubit is also 1. So our target qubit will flip as our control qubit is 1, bringing the target qubit value to 0 instead. So what is the significance of entanglement? Well, changing the state of one entangled qubit immediately changes the state of the qubit that it is entangled to, right? So if we have the first Bell state of 50% chance of collapsing into 0, 0 and 50% chance of collapsing into 1, 1, by changing the state of one of these entangled qubits, we also change the value of the other, as if the first qubit is 0, then the second qubit must also be 0, and if the first qubit is 1, then the second qubit must also be 1 as well. Additionally, knowing information about one qubit can let us know of the states of other entangled qubits. This is what I mentioned in the entanglement overview at the beginning of the lecture. Adding more qubits also increases the processing power of quantum computers exponentially due to entanglement. This is because of these two previous reasons that I mentioned about the significance of entanglement. And finally, entanglement, as an example, is used in applications such as superdense coding and quantum teleportation, showing its usefulness in quantum computing's applications. Next lecture, we'll be talking about our final quantum mechanical phenomena that allows quantum computers to gain an advantage over classical computers, which is interference. So stay tuned for that, and see you next time. Thanks, everyone.